In this video, I'm going to be solving a problem that has to do with an open channel that's at an angle that has water flowing down it. So this is a rectangular channel, so I'm going to start by defining the channel and then talk about what we need to solve for. So it's just a rectangular channel with water flowing through it. So this is a side profile of the channel. It has a width of W and then a height of water H. And so if we look at it from a side view, the channel is at an angle with the horizon, and it's an angle of theta. So you can kind of think about this as the sidewall of the channel, and there's water flowing downhill through the channel. And then the length of the channel is defined as delta x. So in this problem, we are given W, the width of the channel, and that is 0.5 meters. We're given theta, the angle that the channel's at, which is 15 degrees. And we're also given the volumetric flow rate of water going through the channel, which is 1 meter cubed per second. And so the objective of this problem is to find the height of the liquid as it flows down the channel. And so how we're going to do that is I'm first going to write down Bernoulli's equation, and we'll make a few assumptions along the way, and we'll be able to code this end equation into Python and solve for our height. So starting with Bernoulli's equation, so I went ahead and wrote it out. Instead of using the coefficient of friction, I wrote it out in terms of the fanning friction factor. And now we kind of have to think about this and apply it to our problem. So since our channel's open, the pressures at both points, so if we define this as 0.2 and this is 0.1, the pressure at both of the points is the same. So this term is going to be 0. For this second term, we also don't need to worry about it because there's no change in velocity down our channel. It's going to be a steady flow of water. There's no change in diameter of it, so the velocity is going to stay the same through the whole channel. So this term is also 0. And so what we're left with is this term here. And we can actually rewrite the change in z using theta. And that's going to look like this. It's just a simple trig function. So the delta z is going to equal delta x times the sine of our angle. And that will give us the distance between 0.1 and, or the vertical distance between 0.1 and 0.2. So I'm going to go ahead and rewrite this equation, substituting this expression for z1 minus z2. And the right side of the equation is unchanged. And now we can go ahead and cancel the delta x that's in both sides of the equation. So from here, our next step in solving this problem is finding the shear stress on the side of our channel. And we can actually do this by making an assumption that this shear stress on the side of a circular or a cylindrical pipe is representative of the shear stress on the side of the channel that we're working with, because calculating the shear stress on the side of a rectangular pipe is extremely difficult. So we're going to go ahead and make this assumption to simplify the problem a little bit. So now we need to find the shear stress for a cylindrical pipe. And so the pipe is going to be completely filled with water, and we have flow going downward. The pipe has a length of delta x. And instead of calling it the height or anything, I'm just going to leave it as delta x because it'll be less confusing when we go ahead and apply this equation to our rectangular channel. So now the first step in this is to get a force balance. So the weight of the fluid in the pipe is balanced out by the force caused by the shear stress on the sides of the pipe. So to get at the weight, it's just going to be mg. Well, we don't have the mass of liquid in the pipe, but we can calculate the volume. And since it's just water, we know the density. And so from here, it's just going to be rho, the density, times the volume, which is the cross-sectional area times the length of the pipe, delta x, times g. And so now, like I said, this is equal to the force caused by the shear stress on the pipe. And so it's going to be the shear stress multiplied by the area that's in contact with the liquid. And so I'm going to go ahead and define something called the wetted perimeter, which in this case, it's just the circumference of our circle. And this will be multiplied by the length of our pipe. And so this gives us the total area that is touching the water. And so from here, we can go ahead and simplify this equation a little bit. So the delta x's cancel on both sides. And I can go ahead and move this area to the right side of the equation. So we'll have rho times g equals tau times the wetted perimeter over the area. And then from here, to continue on solving for the case of this circular pipe, I can actually go ahead and rewrite this ratio of the wetted perimeter to the area using the actual values. So the perimeter, like I said before, is just the circumference. And so it's just going to be pi times the diameter. And then the area, it's just going to be the cross-sectional area of the circle. So pi times d squared over 4. And so if we simplify this expression, it ends up being 4 over d. The pi's cancel out, the diameter cancels out with one of the diameters in the denominator, and since this fraction's in the denominator, we just need to flip it. Now from here, I can go ahead and plug that expression in here. And then I'm actually going to go ahead and move rho to the other side of the equation, and then we'll be able to plug it back into our adjusted Bernoulli's equation that we created at the beginning of the problem and solve for the shear stress. So moving rho to the other side, we get 4 times tau over rho times d. And then we can go ahead and plug this into this equation for g. So we have our expression for g times the sine of theta, and that is equal to 4 times the fanning friction factor times v squared over 2d. Now I'm going to go ahead and give myself some more room so I can simplify this equation. And so to simplify this bottom equation, I'm just going to solve for tau. So start. Divide by 4. That's going to give us just a 2 in the denominator. These will cancel out. We'll have the fanning friction factor. We'll have velocity squared. The diameters cancel out. And then multiply rho over to the other side. And then we divide by sine of theta. So this is the expression for the shear stress on a cylindrical pipe. We're going to go ahead and assume that this expression also represents the shear stress on the edge of our rectangular pipe. And from here, we can go ahead and continue to solve this problem. So I'm actually going to reuse this equation that we calculated that we used earlier right here. And instead of applying the geometry of the cylindrical pipe, I'm going to apply the geometry of the channel. So now that we know tau, we can plug that into our equation as well. So we get rho times g equals rho times f, the fanning friction factor times velocity squared over 2 times sine of theta. Now we need the wetted perimeter, but this time it's for our channel. And so to get at that, it's just going to be 2 times h plus w, because that gives us this perimeter where the water is touching, and then divided by the area, which is just h times w. So from here, we can go ahead and cancel out the rows on both sides. And we're actually almost done deriving the equation we need to solve this problem. So we know theta, that was given. We know w, that was given. We know h, well, h is what we're looking for. And so the two terms that we're left with are the fanning friction factor, F, and the velocity. So since we're given the volumetric flow, we can actually find the velocity. It's just going to be Q equals the velocity times the area, which in this case is just h times w. And so we can rearrange this and solve for v, and then plug it into our equation here. So it's going to give q squared in the numerator times 2h plus w divided by 2 times, well, we already have an h times w in the denominator, and then we're dividing by h times w squared, so this becomes h times w cubed sine of theta. So now the only piece that we're missing is the fanning friction factor, and we can actually use Churchill's equation like we used in previous videos to calculate it. But in order to use this equation, we need the Reynolds number. And so if you remember, Reynolds number is rho v d over mu. But we really don't have a defined diameter for our square pipe. And so we're actually going to use, again, kind of compare this to a cylindrical pipe and find the diameter that kind of represents in this problem. So if you remember, the ratio of the wetted perimeter to the area for the cylindrical pipe was 4 over d. If we set that equal to the wetted perimeter divided by the area of our channel, we can go ahead and solve for d and then use this value to compute the Reynolds number. And so just quickly doing that, just some more algebra, we get 4 times hw over 2h plus w, and so this becomes the diameter that we're going to use. So now from here, we have all the pieces we need. We just need to move to Python and code it. So now that we have the equations from the whiteboard to solve this problem, all we have to do is just go ahead and code them into Python. So I went ahead and typed out the two import statements we need. So I've imported numpy and I imported root from SciPy Optimize. I also went ahead and typed out the kind of couple properties of water, so the density and the viscosity, and I also typed out the acceleration due to gravity. And then I went ahead and copy and pasted the code block from a previous video for the Churchill function that we'll use to calculate the fanning friction factor in a little bit. And so now from here, the next step that I need to do is go ahead and define our knowns. So we're told that the width of the channel was 0.5 meters. We were told that the volumetric flow rate is 1 meter cubed per second. And we are also told that theta is equal to 15 degrees. And we have to go ahead and remember to convert this to radians. So now from here, we can go ahead and start to put together our function that will pass to the root solver. So I'm just going to define it as equation, and we'll pass the vector of unknowns. In this case, the only unknown in our vector is h, and that's what we're solving for in this problem. Now from here, we just need to code out a couple equations. So I'm going to go ahead and start with coding out the diameter, which is this bottom right-hand equation here. So d is going to be equal to 4 times the height times the width of our channel divided by 2 times the height plus the width. And then next, I'm going to go ahead and calculate Reynolds number. So that is just rho times v times d over mu. Now we don't have the value for v yet, but we can go ahead and calculate it first from q. So v is going to be equal to q divided by the area, which is just h times w. Now from here, we're ready to calculate f using Churchill's equation. And so we need to pass the Reynolds number, and we also need to pass the surface roughness. So for this problem, I'm just going to put a very low surface roughness. I'll go 1 times 10 to the negative 6, so that way we're kind of calculating it with a pretty smooth channel. And then from here, I think we've calculated all the variables we need for this equation, so we can go ahead and plug it in. So how we're going to write this out in our root solver is we're going to subtract the acceleration we're going to take the acceleration due to gravity and subtract this function from it. Because when we find the proper value of h, it'll equal 9.81. And so this will go to 0, and the root solver will return the answer that we're looking for. So just have to go ahead and type this out. So we have f times q squared times 2 times h plus w. This is divided by 2 times h times w squared times the sine of theta. And so from here, I need to make sure that we return this as an array, and then we can go ahead and test and see if this works. So all we need to do is implement this into the root solver. So we'll pass our equation that we wrote, or the function that we wrote, eq, and then we'll go ahead and pass an initial guess, which I'm just going to go ahead and guess 0.2. And I got some error. Let me double check to make sure that I have this equation written in properly. So we have f times q. All right, so I had the wrong exponent. Let me see if that was the issue, and that was the problem. So now the root solver ran successfully. We can grab the x attribute out of it, and this is our answer. So when we have a volumetric flow rate of about 1 meter cubed per second in the channel, then the height of the fluid is going to be about 0.1 meters or 0.14 meters.